Hello and welcome. In this video, we're going to take a look at what is perhaps one of the more intuitive uses of the definite integral. And it's actually just taking a look at the average value of a function over an interval. Now, when we think about average, a lot of times what we're thinking about is probably having a set of data, so a bunch of values, and we want to find an average. And what we usually use to calculate that is the arithmetic mean, which is nothing more than our common method of adding all of the values together and dividing by the number of values. But now we're talking about a function. A continuous function in particular is something that could be just increasing and decreasing, rising and falling. I want to try to find an average of that whole interval. Now, being a function over an interval, there are infinitely many points on this function in that interval. How do we go about trying to find the average? Well, what we can do here is a function, and I've got maybe the x-axis, but it could be in terms of time or whatever. And you can see it's increasing and decreasing. What if I want to focus on this interval from 5 to 15? Well, there's definitely points where it's lower than others. So we have a maximum value and we have a minimum value for sure. That just comes from having a closed interval with a continuous function. Think back to the closed interval method for optimization. But we want to find an average, so it's going to be somewhere between maximum and minimum. We could represent that as being maybe a horizontal line here somewhere. Definitely not going to be as low as 5 or as high as 15. It's going to be somewhere here in the middle, let's say somewhere around there. Okay, well, how do we find this line? Well, we go back to basics, and let's imagine that we can just take several little points here as being samples, and each of those being some sort of value y on this function. And if we take many, many points, then we can simply take the average of them. Let's call these sample points. Various different values of x that we're going to plug in and see what the function equals at each of the points. Now, we can use as many as we like. It makes sense here to start off with just some sort of fixed number, let's say n. What we'll do is we'll take this interval and divide it up equally into n equal subintervals. Now, this is going to sound familiar. We might remember how to calculate the width of each of those subintervals when we go back to our definition of the definite integral. Thinking back to an area problem, delta x was just equal to b minus a, the width of this interval, divided by n. Now, each of those subintervals, if we think about having n points as just being x0, x1, x2, then we have a formula that carries over as well. The endpoints of each subinterval can be listed as xi, where xi is simply just this formula a plus I times delta x. And we're going to start at I equals 0. That means that x0 is simply a, which would be 5 here. And if we go all the way up to n, then xn is going to be a plus n times delta x. Given the formula for delta x here, that's going to just equal b, which is 15, for example. So these x0, x1, x2, the endpoints of every intervals. The first interval would go from x0 to x1, and the second interval would go from x1 to x2, and so on. Now, in each of those intervals, we're going to need to pick a value for x. And we're going to plug that value of x in, figure out what the function equals. So we'll start by picking an arbitrary xi star in each interval. It could be the left, it could be the right, or even midpoint of each of those intervals, but it doesn't really matter so long as we pick a point in each of these equal subintervals. So that's going to give us x1 star, x2 star, all the way up to xn star. Now, we've got this xi star. We're going to plug that into our function and see what the y coordinate of that point is. And we're going to take the average of all of those y values. Now, we do this using our formula for the arithmetic mean. Plugging each of these xi stars into our function f. We're going to add all those values together. There's n of them, numbered from 1 to n, and we'll divide that by n. And there's a couple different notations that we often use for mean or averages. The mean of something, we often have a little bar over top of the quantity. So if we're treating f as a quantity, then it makes sense to have f bar. However, we're still thinking about f as being a function, and sometimes it makes a little bit of sense just to say f average. That would also be equivalent notation. It doesn't really matter. But over on the right-hand side, this 1 over n is something that we can pull out front and make this into a nice compact sigma notation. we can really just rewrite this as 1 over n times the sum of the f of xi star values from I equals 1, n. Now at this point in time, remember, if delta x is b minus a over n, we have 1 over n, then we can use the reciprocal. This 1 over n is simply delta x over b minus a. And if we want to plug that in, this is going to look pretty familiar. Here I have the 1 over b minus a, and the delta x I'm just simply putting to the far right-hand side. And that is going to look very familiar, I hope at least anyways, because this is going to be the part of the definite integral that we were looking at called the Riemann sum before we took the limit as n goes to infinity. And spoiler alert, this isn't exactly the average. This is the average of those n points, but it's not the average of the whole function. We actually do need to take the limit as n goes to infinity, and that's how we're going to get definite integrals. Taking the limit as n goes to infinity now, to get the proper f average, then we will have to look at this quantity and see what happens as n goes to infinity. Most of it is very familiar, except for this 1 over b minus a. But luckily, that is written so that it does not depend on n at all, and as n goes to infinity, this is a constant that can be moved out front of the limit by limit laws. That leaves us with a definite integral. And so finally, the proper formula to get the average value of a function over the interval is simply just the definite integral of the function over the interval, and then divided by the width of the interval. All right, well now we know how to calculate the average value of a function. Let's take a look back at that example up here. We've got this visualization of that horizontal line. That's our average value. That's just y equals the average value. And you can see that our function is sometimes below the average and sometimes above the average along that interval. Well, since we have a continuous function here, it would make sense that by the intermediate value theorem, at some point in time, our function has to be equal to that average. Sort of like the chicken crosses the road theorem. You know, the chicken crosses the road because it was on one side and then it was on the other side. Well, that's the same case with our function. It can't be always above average and it can't be always below average. So long as the function is not constant, which would be pretty boring, then it's going to be at some point above and some point below the average, and it would have to equal the average value in the interval. That gives us the mean value theorem for integrals. And so, the mean value theorem for integrals says that if f is continuous on the closed interval from a to b, then there would have to exist some sort of number c, where c is in that interval, such that f at that point c is equal to this average value. And of course, f average is just given by that brand new formula involving the definite integral. Okay, well, I like to always rearrange that a little bit and think about it this way. fc, which of course is just average value, times b minus a is equal to the definite integral. And we know how to interpret the definite integral as just being the area under the function. But on the left-hand side, f of c times b minus a, we want to picture that that's the width of the interval multiplied by a height. And so really it's an area of a rectangle. So going back up here to this picture, we can imagine that the area under our function, whether or not that has any sort of physical interpretation or not, that is equal to the area by this average value giving us a rectangle. Those would have to be equal areas. We're essentially taking all of this extra area up here and we're pouring it into this area. It should fill it up to make a perfectly horizontal line, which gives us the average value. That's kind of how I like to think about it a little bit. Now, let's try an example out where maybe we'll take a look at some physical quantity here. We'll take a look at its average value and apply that mean value theorem for integrals and find out when that function is equal to its average over the interval. All right, in this example, let's take a look at a velocity function. Here, let's say the velocity of a car in meters per second at a time t in seconds is given by the expression 2t over the square root of t squared plus 9 for t greater than or equal to 0. Now, first of all, let's just try this average function formula out. Let's see if we can find the average value of this function, which would give us average velocity. Let's do that over the first 4 seconds. But then let's apply that mean value theorem for integrals and see at what time during this first 4 seconds would the instantaneous velocity equal to that average from part A. Well, to calculate the average velocity, we would look at the average value of this function from 0 to 4. And when we do that, we have to make sure that we look at the definite integral and divide by the width of the integral. And it might make sense to call this v bar or maybe v average. Okay, now for this particular definite integral, we're going to need a substitution. If we choose u to equal t squared plus 9, then we can see that that's going to be a good choice for the substitution since our derivative, du by dt, is equal to 2t, which is what we have in the numerator of our fraction. It is better often to just rewrite that right away in differential form, and it can be kind of handy to think about that as being a replacement for dt, which is simply u over 2t, and that's going to cancel the 2t in our numerator. But let's not forget that this is also going to affect the boundaries of our integral. Changing the variable from t to u means that t equals 0 and t equals 4 are no longer relevant. We need to figure out what u is going to equal. Well, when t equals 0, u is going to equal 9. And when t equals 4, then that is going to correspond to u equals 25. Now, let's make all of those replacements. And we'll notice that this 1 over 4 isn't going to be changed whatsoever by the substitution since it's not even part of the integral. But now, our new integral, changing the color here to blue, is going to have the boundaries 9 and 25. 2t comes from our previous integrand, but it will soon get canceled out when we replace dt with du over 2t. And that is really the only way that we're going to get a successful substitution is by changing the variable completely. Now, it's at this point in time that 1 over the square root of u should just be written as u to the negative 1/2. And we can apply the power rule and plug in our endpoints 9 and 25. Raising the power by 1, we get 1/2. Dividing by 1/2 is the same thing as multiplying by 2. So the antiderivative that we will use is 2u to the 1/2. Don't need a plus c for this definite integral. We just need to plug in u equals 9 and u equals 25. Square root of 25 minus the square root of 9. So that leaves us with 1/2 times 5 minus 3, which is 2. That is equal to 1. Now, since this question has units, that means that our average velocity is equal to 1 meter per second for the first 4 seconds. Now, we can tell right away that when we plug 0 into this velocity, our initial velocity is 0. When we plug 4 into this velocity, in the denominator, we're getting a nice square root of 25, so that is 5. That's going to be 8 over 5. Okay, so at some point in there, since this function is continuous, we would have had to equal 1 meter per second, since we ended up starting at 0 and ending at 8 over 5. At some point in time, we would have had to equal 1 meter per second. Let's see if we can figure out what that is. Well, we will set v of t equal to 1, and that gives us an equation to solve. Well, we can rearrange that equation, and we can square both sides to get rid of that square root. This becomes a nice, easy quadratic. T squared has to equal 3. Well, remember, we're looking for a time in the interval from 0 to 4, so we're only going to consider the positive root of 3, and that gives us our time. Now, at this point in time, if we want to, we could actually possibly visualize that function, think about the area underneath it, and compare that to a horizontal line v equals 1. And the area under v equals 1 is just a rectangle. That should have the exact same area as the area under our velocity. So why don't we take a moment just to kind of look at that. All right, here I have just plotted that velocity function in Maple. And we can understand that the area under that function, 0 to 4, since this is with respect to the t-axis, that area would represent displacement. Now, we did actually calculate that particular area back up here in this line. That area was 2u to the 1/2 evaluated from 9 to 25, and that would end up giving us 4. So this is actually a displacement equivalent to 4 meters. And our average velocity we just found was equal to 1 meter per second. And now, if you wanted to take a look at the area under that average velocity over the course of 4 seconds, we should see that this is simply a rectangle with a height of 1 and a width of 4. And that is also equal to 4 meters. So the area of the blue rectangle and the area of the red shaded area both correspond to the same displacement. However, the car chose to accelerate and not be at a constant velocity. If it had been at a constant velocity, that velocity would have had to be 1 meter per second for it to travel the same distance. So that hopefully kind of gives you a little bit of an interpretation about that average velocity and the corresponding areas that are equal to each other. And there we go. That's fairly intuitive as far as some applications go of the integral. We can just take all of our little points along the curve and estimate the average by adding them up and dividing by n. But as it turns out, if we want infinitely many points, that just becomes the definite integral and then divided by the width of the integral. So we can always use that to find the average value of a function over an interval, so long as it is at least continuous or piecewise continuous. If it has any sort of crazy asymptotes or other kinds of discontinuities in there that we can't integrate, that's when this method would fail. And that's when the mean value theorem for integrals wouldn't be able to apply. Well, we'll take a look at some other applications in the future, as well as taking a look at some more interesting integrals and how we can tackle those. Thanks for watching, and I'll see you in the next video.